Alright, so this is the 10th video in the series of name reactions, and today we are going to discuss about Baeyer Villiger oxidation. So in this reaction, we convert aldehyde or ketone into an ester, right? So we convert the aldehyde or ketone into an ester. So when you have a hydrogen, that is what we call aldehyde, and when you have a R group, any alkyl group, that is what we call the ketone. And you convert your aldehyde into an ester. This is what we call the Baeyer Villiger oxidation. To bring out this change, you can either use m-cpba or you can use hydrogen peroxide, or you can use trifluoroperoxyacetic acid. So use any one of them. You can use m-cpba, hydrogen peroxide, or trifluoroperoxyacetic acid, and you will be able to convert your aldehyde or ketone into an ester. That is what we call the Baeyer Villiger oxidation. You will also need, you can do this reaction either in acidic condition or under basic condition. So you need any one of these reagent in presence of either acidic or basic media. So let's go ahead and draw the mechanism by using each and every reagent under acidic or basic medium and convert aldehyde or ketone into an ester. Okay, so let me take my ketone as acetone. Okay, and I'm reacting this with hydrogen peroxide under acidic media. And I know this is a Baeyer Villiger oxidation, so the product will be an ester. So feel free to pause the video and try the mechanism for this particular reaction. Okay, so let's begin. So we have a ketone and we have a acidic media, we have hydronium ions. So this oxygen with its lone pair will grab this proton, will neutralize oxygen, and now we have activated the carbonyl system. Now we have H2O2. So one of the oxygen will attack at this carbonyl system, will neutralize oxygen, and this will give me. So we have now OH. Here we have O bonded with O and another H, and this oxygen also contains one hydrogen. Overall 3 bonds, so we'll get positive charge. Right? So we have just removed water. Now that water can come back, can grab this proton, will neutralize oxygen. So we have this one. Now at this point of time, so this oxygen grab this hydrogen and becomes hydronium ion once again. So this oxygen can take this proton, can remove water molecule, and becomes H2O+. So now we have a leaving group in our system. So whatever water molecule just left will come back, can take this proton. This bond will form double bond here, and this methyl group will migrate to oxygen and will eliminate water molecule. So this is a key step. So this water molecule grabs this proton, this bond forms double bond here, this whole group, this methyl group migrate towards oxygen by eliminating water molecule. So now we have the product we are looking for. Okay, so we have a carbonyl system, and now this methyl or this carbon is bonded to oxygen. This is what we have here. So this is the mechanism of Baeyer Villiger oxidation by using hydrogen peroxide under acidic media. Okay, now let's do the same reaction under basic condition. So we have a ketone as acetone. We are using hydrogen peroxide under basic condition HO minus. So we have hydroxy ion as our base, and the product we are getting is a ester. So feel free to pause the video and try the mechanism for this reaction. Okay, so we have a hydrogen peroxide and we have a basic condition. So this HO minus can take this proton and this bond pair will fall on oxygen. So we have this particular system. We have an acetone and we have recently generated this one. So this will come into picture now. This will attack at this carbonyl center, breaking this C double bond O bond, and this will give me oxygen with negative charge. Here I have bonded with oxygen, so this is O, O and H, right? So we just removed water molecule here, that can come back, and this oxygen can take this proton, eliminating HO minus, giving me oxygen bearing negative, oxygen, oxygen bonded to two hydrogens with positive charge. Now at this point of time, we know what is going to happen. This oxygen will reform a double bond. This methyl group will migrate towards this oxygen, and this water molecule is going to be eliminated. And the product we will get is what we are looking for. Right? So we have generated a carbonyl system. Let me number it. So 1, 2, 1, 2. Now carbon number 2 has become carbonyl system. And now this methyl, this carbon has completely moved or migrated, or you can say bonded with oxygen. So this oxygen is number 3, 3. This carbon is 4, which is right here. So this is a mechanism of Baeyer Villiger oxidation by using hydrogen peroxide under basic condition. Now just to add here, you can do this reaction under acidic condition, basic condition, and I have noticed that in some of the books I have referred, people also use Lewis acid. So you can use any one of them in presence of Lewis acid and you will be able to convert your aldehyde or ketone into an ester. So let's go ahead and draw the mechanism when we have a Lewis acid. Okay, so we have acetone. We have hydrogen peroxide with a Lewis acid. So for example, I'm taking zinc chloride, right? And we are getting ester. So the idea of using Lewis acid is simply the activating the carbonyl group, because we know this oxygen can chelate with this Lewis acid. So let me go ahead and write it. So this oxygen can chelate with Lewis acid, and this will get a partial positive charge. Now we have H2O2. So this oxygen, now this carbon is little more activated because of Lewis acid. So this oxygen with its lone pair will attack at this carbonyl system, and this bond will be donated to Lewis acid. So this will give me Now here the intramolecular hydrogen transfer will take place, neutralizing this oxygen, and this will give me oxygen still bonded with Lewis acid, and here we have oxygen, and this oxygen is bonded to 2 hydrogen, giving me positive charge. So now we have a leaving group present in our own system. So this oxygen will break bond with Lewis acid, and this will form double bond here. This methyl group will migrate towards this oxygen, and this water molecule is going to leave. So this is nothing but the same mechanism as previous two, and we will get the product. So this is a Lewis acid mediated Baeyer Villiger oxidation under H2O2 as our oxygen donor species. Okay, let's use the m-cpba. So I have acetone. I can convert this into an ester. I can use m-cpba or trifluoroperoxyacetic acid. The structure of m-cpba is called metachloroperoxybenzoic acid. So you have a benzoic acid, but it is a peroxy one. And at meta position you have chloro. So this is what we call the metachloroperoxybenzoic acid. And this is the oxygen which you see right here. Okay, so if I label this oxygen 18 and this oxygen 18 in the product, this oxygen of ester will be labeled as 18. So you know that this oxygen is what's sitting here. And this reaction can also done under acidic or basic condition. So mechanistically they will be same. So I'm going to show the mechanism for m-cpba in one of them like acidic condition, and for this one I will show the mechanism under basic condition. So let's go ahead and draw it. Okay, so we have this acetone reacting with m-cpba under acidic condition, and we are getting ester molecule. So feel free to pause the video and try the mechanism. So we have this acetone, we have hydronium ions, acidic condition. So this oxygen will take this proton, neutralizing oxygen or eliminating water molecule, and now we have activated the carbonyl system. Now the m-cpba will come into picture. So this is metachloroperoxybenzoic acid, and this oxygen of this m-cpba will attack at this carbonyl system, breaking this bond. So this will give me oxygen, oxygen, C double bond O, benzene, and at meta we have chloro, and this oxygen with 1 hydrogen, getting overall positive charge, right? So we just removed water molecule, that will come, will take this proton, neutralizing oxygen. correct? Now we removed H3O plus, so we have this one. At this point of time, this oxygen will take this proton, neutralizing oxygen. Okay. And this oxygen has 3 bonds, so we'll get positive charge. Now we removed water molecule. So this water will take this proton, this bond will form double bond here, this methyl group will migrate towards this oxygen, and this whole group is going to leave. So this will give me my main product, that is ester, and the byproduct is this one. So this is the mechanism of converting your ketone into an ester by using m-cpba under acidic condition. You install this particular oxygen into an ester, and the byproduct is metachloroperoxyacetic acid. Okay, so let's say I have acetone. I'm using trifluoroperoxyacetic acid. Under basic condition, and we are getting ester. So the structure of trifluoroperoxyacetic acid we have already seen. And we have basic condition. So this base will grab this proton, will generate alkoxy ion. Right? And we have acetone. We just formed this moiety. This oxygen with its lone pair of electron will attack at this carbonyl. This bond is going to break. And we have O, O, C double bond O, CF3. Right? Now we just removed water molecule. So this particular oxygen will grab this proton, eliminating HO minus. Now this oxygen will reform a double bond. This methyl group will migrate towards this oxygen, eliminating this particular acid. So this will give me my product of interest, that is an ester, and the byproduct is corresponding acid group. So this is the mechanism by using trifluoroperoxyacetic acid under basic condition, where you get your ester and the byproduct as trifluoroacetic acid. Now let's solve some practice problems. Okay, so this is very important in terms of your exams. So make sure you take a note for every reaction. So the first example is, let's say I have this molecule. Okay, and I'm doing Baeyer Villiger oxidation by using m-cpba under acidic condition, that is acetic acid. So what is the product? My oxygen will be inserted here, or here. So let's call it as A and this one as B. So two products are possible. Ester can form from left side or from right side. So this could be one product. And this can be second product. So one of them is going to be the major one. So what do you think? Which is the major product? Is it from A side or the B side? So take a note that you have to install oxygen from the side where electron density is more. Okay, so electron density should be more. So in this particular example, we have a ethyl group here and we have a third butyl group here, right? And both are electron donating groups. We have a plus I inductive effect. But the tertiary butyl group has an extra methyl group, so extra electron density will be there. That's why the oxygen is inserted from the P side. So that's why this one is the major product. So always remember that when you get such type of questions, you have to insert your oxygen from more electron density crowd side as compared to the lesser one. Okay, here's the another important note for you. When you have a 1,2 diketone system, so this is a 1,2 diketone system, and whenever you do a Baeyer Villiger oxidation to it, what do you think? What is going to be the product? So you need to know that whenever you encounter 1,2 dicarbonyl system, you have to insert your oxygen between these two and form an anhydride. So this is something important you should know for your exam perspective. That whenever you have a 1,2 dicarbonyl system and you are doing Baeyer Villiger oxidation, always insert your oxygen between these two carbonyl system and form anhydride. So this core is called anhydride. Another example can be So what do you think? What is the product if I subject this particular starting material to the m-cpba or do Baeyer Villiger oxidation? So as discussed, we have to insert oxygen here and make anhydride, and that will be the product. So this is the product for this particular reaction. Okay, so another question. Let's say I have this one. I have a benzene, a carbonyl system, and a methyl group, and I'm doing Baeyer Villiger. So will my oxygen will be here or here? Will it from the A side or the B side? What do you think? So the product will be from the benzene side, because the benzene has more electron density as compared to methyl group. That's why the product will be this one. So insert your oxygen from the more electron density cloud. That's why the oxygen was inserted at this point. Let's solve some more problems. Okay, try this one. Let's say this time I have a benzene, a carbonyl system, but instead of methyl I have tertiary butyl, and I do Baeyer Villiger oxidation. Will my oxygen will go from here or here? So the methyl group has lesser electron density as compared to the benzene one, but the tertiary butyl group has more electron density as compared to the benzene one. That's why the oxygen will be inserted from the tertiary butyl side. And you get this one. Okay, so let me give you another example. So this is my starting material. I'm adding hydrogen peroxide under acidic condition, doing Baeyer Villiger oxidation. So what is the product? Pause the video and draw the product. So two products are possible, one oxygen inserted at left side and one oxygen inserted in right side. So you see this benzene has two nitro groups, both are -I groups, okay? Both are electron withdrawing groups pulling electron away from the center, correct? So electron density is less at this point. So that's why the oxygen will be inserted in the right side and the product will be this one. So all you have to do is always insert the oxygen in the more electron density side and you will be fine. To support my sixth question, let me give you one more example. Instead of nitro groups, this time I am keeping a electron donating group like OMe. And doing the same reaction. So the nitro group was electron withdrawing group, that's why electron density at this center was less. So that's why oxygen was inserted in the right side and we got this one. But look here, the OMe group is electron donating group, making more electron density cloud at this center as compared to hydrogen. So that's why the oxygen will be inserted in the left side and the product will be this one. Okay, here is another question. So my starting material is this particular ketone and I'm doing m-cpba, Baeyer Villiger oxidation. So now this is simple. So NO2 group withdraws electron -I, OMe group donates electron +I. So the one who donates electron will create more electron density. So electron density at this carbon is more. So that's why oxygen will be inserted in the right side. And this is the product. So the electron donating group creates more electron density or the cloud at this center. That's why oxygen is sitting here. Okay, one more example. Let's say I have this one, and I'm doing Baeyer Villiger oxidation. Okay, so we know that as compared to single bond, when it comes to double bond, the electron density or the electron cloud in the pi system is more. So that's why the oxygen will be inserted from the site where alkene is present. And you got the product. So I inserted my oxygen in the alkene site, not in the saturated alkane site, because alkene will have more electron density. Okay, one more example. Let's say I have this particular starting material, okay, where this chlorine, this center is a chiral center where chlorine is present above the plane, and I'm doing m-cpba mediated Baeyer Villiger oxidation. So what is the product? So chlorine is a halogen and it has more electronegativity and will act as a minus I group, will withdraw the electron. So electron density at this center is less and at this center it is more. So the oxygen will be inserted in the more site and rest will be same. So always remember two things, that in Baeyer Villiger oxidation the oxygen will be always inserted from the more electron density cloud site, and second thing is chiral centers will not be disturbed. The chirality will never be disturbed in case of Baeyer Villiger oxidation, simply because the group is getting migrated all over, so chirality will be retained. So chirality never changes when it comes to Baeyer Villiger oxidation. Even if I insert my oxygen at this site, the chirality will not change and this Cl will still be above the plane. Okay, let's say I do not have this chlorine group and I do Baeyer Villiger oxidation. So this time the electron density is more here. So oxygen will be inserted, So oxygen will be inserted from that side and this will be product.